Welcome to Computational Physics. Today we are beginning our unit on numerical integration, specifically focusing on definite integrals, calculating areas, and using the quad function. By the end of this session, you should be comfortable explaining definite integrals as physical accumulation. You will also learn how to distinguish between analytical and numerical methods, apply basic rectangle and trapezoid rules, and confidently use the quad function to evaluate one-dimensional integrals and interpret their error estimates. Let us start by recalling why integration matters in physics. We frequently encounter quantities derived by accumulating small contributions over an interval. For instance, finding displacement from velocity, calculating the work done by a variable force, or determining total charge from a charge density. Since we cannot always solve these integrals analytically, numerical integration becomes an essential tool. Conceptually, a definite integral represents the net accumulation of a function between a lower limit a and an upper limit b. Function values above the horizontal axis add positive contributions, while those below subtract from the total. Crucially, the physical unit of the integral is simply the unit of the function multiplied by the unit of the integration variable. To perform these calculations in Python, we will rely on NumPy for array manipulation and mathematical functions, alongside matplotlib for visualizing our integrands and integration regions. We will also import two specific integration tools from the SciPy library. We will use the quad function for highly accurate one-dimensional definite integration, and the trapezoid function for handling discrete, sampled data. Running these imports prepares our environment, giving us access to the numerical solvers and plot settings we need for the rest of the lecture. Let us start with a simple, known integral to verify our methods. We will integrate the function x squared from 0 to 1. Analytically, we know the exact value is 1/3, which gives us a perfect baseline to test our numerical approach. We define our function, set the limits, and pass them to the quad solver. The quad function returns two values, which are the estimated integral and an estimate of the numerical error. We then print these results alongside our analytical exact value to calculate the absolute difference. The numerical output confirms that the quad function performs exceptionally well. The estimated value matches the exact value to many decimal places, and the absolute difference is on the order of 10 to the -17, which is essentially the limit of machine precision. Before trusting any numerical integral, it is a very good habit to visualize the area being computed. We can set up a plot using NumPy to create an array of x values and fill the area under the curve between our lower and upper limits. Calling the plot display command will render the visualization so we can inspect the shape of our integrand. Looking at the plot, we clearly see the function x squared bounded between 0 and 1. The shaded region represents the accumulated area, which is entirely positive and graphically corresponds to the value of 1/3 we just computed. While the quad solver is incredibly powerful, it is important to understand the fundamental algorithms behind it. Numerical integration generally works by dividing the total interval into many small subintervals. Here, we define a basic left endpoint rectangle rule to approximate the area. We can improve upon the left rectangle rule by taking the midpoint of each subinterval, or by connecting the function values to form trapezoids. We define functions for both the midpoint and trapezoidal rules so we can compare their accuracy against the simple rectangle approach. We then run a loop, increasing the number of subintervals from 4 up to 64. Inside the loop, we compute the area using all three methods and print the estimates to observe how they change. Notice how the estimates behave as the number of subintervals increases. The left rectangle method approaches the true value of 1/3 rather slowly. In contrast, the midpoint and trapezoidal rules are much more accurate even with a small number of intervals, quickly converging to the correct mathematical answer. To understand why these methods differ, we can visualize the rectangle and trapezoid approximations. We will use a very coarse grid of just 6 subintervals to make the geometric differences obvious on our plot. We plot the true function curve overlay the left-aligned rectangles, and explicitly mark the sample points that the trapezoidal rule would connect with straight lines. Geometrically, you can see that the left rectangles systematically underestimate the area for this continuously increasing function. The trapezoidal rule, which connects the orange dots, follows the curve's shape much more closely, explaining its superior accuracy. We can quantify this improvement by plotting the absolute error against the number of subintervals on a log-log scale. We calculate the errors for all three rules across a wide sequence of interval counts. Displaying this plot will clearly reveal the convergence rates, showing us how rapidly the error shrinks for our different numerical methods. The plot demonstrates that as we increase the number of subintervals, the error drops for all methods. However, the lines for the midpoint and trapezoid rules are steeper than the left rectangle line, meaning they converge much faster and are more efficient choices for integrating smooth functions. Now that we understand the basics, we can look closer at SciPy's quad function, which uses advanced, adaptive techniques. We will integrate a new function, sine of x plus cosine of x, evaluated from minus pi to pi. We pass our new function and limits to the quad solver, extract the estimated value and error, and then set up a plot to explicitly shade the positive and negative contributions over this interval. The numerical output gives a value very close to 0, specifically on the order of 10 to the negative 16. The estimated numerical error is slightly larger but still tiny, confirming that the integral mathematically evaluates to 0. The plot beautifully explains this result. The positive shaded area exactly cancels out the negative shaded areas over a full period of these trigonometric functions, resulting in 0 net accumulation. Let us apply these tools to a physical example, specifically calculating the work done by a position-dependent force. The force function consists of a constant term multiplied by 1 plus a quadratic term, scaled by an exponential decay. We want to find the work done moving a particle from 0 to 2 meters. We define our physical constants, write the Python representation of the force function, and evaluate the integral. Then, we plot the force against position and shade the region corresponding to the total work done. The output tells us that the work done is approximately 16.9 joules. The extremely small numerical error gives us great confidence in the computational evaluation of this physical system. Visually, the force curve shows a slight initial dip before rising, and the shaded area is the total work done. The entire curve stays positive over this domain, meaning the force is continuously doing positive work on the particle. It is essential to remember that the computed number has direct physical meaning. By dimensional reasoning, multiplying the y-axis units in newtons by the x-axis units in meters confirms our resulting area is in joules. Always verify the dimensions of your plotted integrals. Sometimes our integrand requires extra parameters that are not the integration variable. For instance, the Bessel function of the first kind depends on an integration variable t, but also has fixed parameters for the order n and the position x. We can pass these fixed parameters to the quad solver using the args keyword argument. Here we compute the 0th order Bessel function at an x value of 2.5 using our own integral formulation, and compare it to SciPy's built-in Bessel function. We then generate a plot comparing the first few orders of the Bessel function over a range of x values to observe their characteristic oscillatory behavior. The text output shows that our manual integral perfectly matches the specialized SciPy function. The absolute difference is practically 0, proving that the quad solver correctly handles extra parameters passed through the args argument. The resulting plot displays the decaying oscillations of the Bessel functions. Notice how the 0th order function starts at 1, while the higher orders start at 0, which is a vital physical property in wave mechanics and heat distribution problems. Now it is your turn to practice. I encourage you to modify the limits and functions in this starter code. Try integrating a higher order polynomial and comparing the basic trapezoidal estimate to the exact analytical answer. The loop provided here evaluates the trapezoidal rule for 10, 100, and 1000 intervals. It then compares those basic estimates against the advanced quad function and the exact analytical solution. Running this code shows that the trapezoidal error drops systematically as the number of intervals increases. However, the quad function immediately gives a highly accurate result, demonstrating why it is our primary tool for well-behaved physics functions. To summarize, we have seen that definite integrals represent physical accumulation, and we can compute them accurately using SciPy's quad solver. Plotting the integrand and checking units are vital habits. In the next part, we will explore integration of sampled data and handle more complex numerical scenarios.